Welcome back, kids. I know that you have learned so many things in the previous sessions, and today we are going to learn something very, very interesting. And the topic is weightlessness. You are going to learn that how astronauts float in space and how gravity works upon them in space. So, we are going to learn so many interesting things today. I hope you will find it interesting, and I am sure that you guys are going to love it. So before going into weightlessness, first let me ask you that what is mass and what is weight and how they are different. So basically, mass is a measure of matter, whereas is weight is that weight express the measure of heaviness in a body. So let me make it more clear by giving an example of tug of war. I know that all of you love tug of war, and I'm sure that you must have played it very well. Imagine a situation in which there are two people having same strength, okay, and you both are playing the game of tug of war, and one of them, both of you are pulling each other towards each other. So in this game, what do you think who is going to win? Because you both have same strength, you cannot decide that who is going to win because you are having same strength, so you are applying same force towards each other, so none of them of you will win. Now imagine a situation in which one person is weaker and the other person is stronger than you. Then in this case, the stronger person will win, of course. Now imagine a situation in which on one side there is elephant and on the other side there are few persons who are pulling elephants towards themselves. As elephant is stronger than the other person, elephant will pull the other persons towards itself. This is the same concept which works on our earth too, which we name it as gravity. When we throw something up, it comes back towards earth, right? So why do things fall back down on earth? Do we know that? I'm sure that you have learned it. This is because of gravity. So gravity is something which is gravity is an attraction force which between two masses. That is when it is an attraction between two distinct masses, and when the mass of a body is greater, then greater is its pull. So in the case of tug of war, as we saw that the mass of elephant is much stronger than the other person who are pulling him. So that is the reason why elephant was able to pull them towards itself. Now you must be wondering that are magnetic force and gravitational forces alike? So maybe yes and maybe no. Yes, because unlike just like magnets, gravity also attracts everything. But in case of magnets, magnetic force only attracts metals. And in case of and no, because unlike gravity, magnets only attracts metal, and whereas gravity attracts each and every body. Moreover, magnets only function when they faces on the same side. That is, they have the same faces facing towards each other. Let me demonstrate you with by giving you an example. I'm having two magnets within my hands. If I try to make them attract, then they will attract. These are the opposite faces, and hence the magnets will get attracted. But if I change the position of my magnets, then they are not going to attract, they'll repel. But this isn't the case in the case of gravity. Gravity attracts each and every faces of the bodies. It won't see that how is it in the opposite face or is it in the same face. It won't see like that. It will attract each and everything. So when we now you must be wondering that how the celestial objects works in space in the outer sky. Why don't they fall onto Earth? Do gravity work in space too? You must have having these questions too. So this concept work over there too. But The thing is, as we know that sun is very very huge compared to earth, hence its mass is very very big and it's very massive in comparison to earth. Hence its gravitational pull is also much much better than earth, and this is the reason why all the planets including earth tends to keep orbiting around sun. So the gravitational force from the sun keeps them in their orbit and they don't fall towards earth. So this is the reason why we don't jump into space very easily. Now you must be wondering that how we can float, how we can jump on different planets, and how the height differ on different planets. So let me demonstrate you by giving some examples. On earth there is gravitational pull, and hence we cannot it is present in on every planet, but in case of earth, we cannot reach up after certain height. That is, after we jump we cannot reach up to after some certain height. As compared to moon is much smaller than earth, and hence we can rise above certain level as compared to earth. Like, if for example, if we are able to jump on earth for, let's say, 5 feet, then we will be able to jump on moon above 5 feet, because the size of moon is smaller compared to earth. Whereas on Mars, we will be able to join much more height than earth. But as Mars, the size of Mars is much smaller than earth. Let's take an example of a comet, which is very small, or and have a diameter of, say, let's say, 2 kilometers. So if you jump on that comet, then you will lost into space forever. Now imagine a situation of tug of war when there is no other person on the other side to resist you. That is, imagine a tug of war that you are playing all alone. There is no other person on the other side to pull you towards itself. So there won't be any other person to resist you or to pull you towards the other side. Okay, so that is the reason that you won't be able to then you won't be able to, uh, there won't be any other person to resist you. So this is the concept of weightlessness, and I want Tejas to continue further from here. Tejas, can you continue from here?
Yes, Zubiya teacher, thank you so much for teaching us about the difference between mass and weight, and you also taught us about how high we could jump on different worlds. Before I go into answering this question, what will happen if there is no one to resist on the other side? Let me recollect the topics that Zubiya teacher taught us. She taught us that mass is different from weight. Why is that? She told us that mass is it's a measure of how much matter is present in a particular object, whereas weight is a measure of how heavy a particular object is. We will learn about why mass and weight is different once we learn the concept of weightlessness. Before going into that, let me answer this question of what will happen if there is no one to resist in the game of tug of war. You see, I have a rope here, so I am stretching it using both my hands. So if I leave one of my hand, you see that there is no tension being built in this rope. So which means that as in when I move my hand, the thread follows in the same direction. If I go somewhere like from up to down, top to bottom, the thread follows the same direction. If I go from bottom to top, the thread goes in the same direction. It is like my hand is trying to pull this thread along the direction wherever it goes. So we know that Earth is rotating around the sun, which means that Earth is also pulling us along with itself as and when it revolves around sun. But what if, while instead of Earth pulling us, if there was nothing to resist us, that is, if I have this ball when it is falling down, until and unless I have my hand to obstruct it from falling down further, you see that the ball keeps falling. What will happen if there is nothing to resist us? Right now, I'm sitting on a chair. I feel that all my weight is concentrated on the seat. On the seat that I'm sitting, I'm exerting some force, and the seat is exerting that force back again on me. I feel that I'm being resisted from going down. This kind of resistance is what leads to a sensation of having weight. That is, you being not able to move from a particular place or being feeling heavy. The sensation of feeling heavy is what we call as weight. However, when if you have ever tried to swim in a swimming pool with your uh, swimming tubes on, you find that you will be floating. You feel very light in water. It is so because when you are in water, you feel that your all your body mass, the weight of your body is being distributed equally all over the surface. That is, the pressure that is being exerted by the water on all the sides of your body, or on all the faces of your body, is almost equal. So you feel that you feel very light. Whereas when I'm sitting right now, or when I stand on a particular weighing scale, I find that I'm very heavy. I find that all of my force is being concentrated on a particular region, so I find myself heavy. Imagine another case wherein we take a spring balance to measure the weight of an object. So we know that the mass of this ball will never change. So if I have a spring weighing scale to measure the mass of this ball, I'll find that on holding that spring measure, it will read. It will give a certain mass. What happens if I don't hold it at the top? What happens if I leave the spring loading at the top? It will just fall. While falling, it won't show any reading. The reading will read as zero. Why is that so? Does it mean that while falling, the ball loses its mass? Actually, not. The mass of the ball remains constant. But while falling, as there is no force to resist this ball from falling, we don't exactly experience how much heavy this object is. We get to know whether this object is heavy or not only when we try to resist it from falling towards ground. So the concept of weight comes only into picture only when there is some resistance that is being offered to the body in the direction of its motion. So, Tejas, what are you trying to say? Is gravity absent in space? Is gravity responsible for weight? If gravity is responsible for weight, how are astronauts able to float around in space? Well, as Zubiya mentioned, gravity is present everywhere. I'm sitting right now in front of your screen, and you all are sitting at your home and watching this particular session at your own comfort. Do you know that by moving this ball from here to here, I'll be exerting some gravitational force upon you? Oh, how is it possible, Tejas? You moving a ball there and we experiencing a force sitting at our places? That is not possible. You're talking all lies. How can I believe you? I'll explain it to you in an easier fashion. Let's say, as Zubiya was talking about the game of tug of war, we have two people who have equal strength. So when these two people try to pull each other, we don't see much difference in their position. However, when these two people are trying to pull each other and a third person tries to pull them in the opposite direction, we find that both of them are dragged towards the third person. So this is the very case that happens even on Earth. As Earth is very huge and it's very heavy, the gravitational force that we exert on each other becomes very negligible. The gravitational force that is exerted by the Earth, the gravitational pull that Earth exerts on us, is much more evident than the pull that we exert on each other. That is the reason we don't see the difference on moving objects around us, the gravitational pull exerted by other objects around us. However, as astronauts are far away in the sky, the gravitational pull exerted by Earth on astronaut is little, but it is not absent. That is not the reason why astronauts float around in space. In fact, they don't have anything to resist while they are in space. While they are in space, they are under what is called as a continuous fall. As they are falling towards the earth continuously and there's nothing to resist them, they don't have any contact force that they're experiencing. That is, There is nothing to resist them from falling towards earth. So that's the reason they feel very, very light. So Tejas, do you mean that if we fall forever, we will be weightless? So I can eat how much ever I want and I'll still be very light? No, on eating how much ever you want, the chances are your mass will increase, but the weight depends upon the pull exerted by the planet. As Zubiya mentioned earlier, it depends on what is the size of the object that is trying to pull you towards you. If the earth is very huge, and that is the reason we can't jump to a very great height. Whereas when it comes to moon, the mass of the moon is very less when compared to earth. That is the reason we can jump to a greater height on moon. And when it comes to comets, which are very, very small compared to earth, we'll be able to jump so high that we will just jump off into space. But however, the pull exerted, this explains that the pull exerted by each body or each celestial object is different from each other depending upon the masses. And that is the reason why a person on Earth who weighs somewhere close to 100 kgs weighs somewhere close to 19 to 20 kgs upon Moon. It is not that their mass is changing. It is just that the pull exerted by Moon is very less compared to that of the pull exerted by Earth. Imagine a case wherein you're holding a hot air balloon or something like a helium balloon. If you're holding a helium balloon that can lift your weight up, you go and stand on a weighing scale, you find that your weight becomes very less. I'll explain it to you in a simpler fashion. Let's consider an object. Let's say this ball. Let me tie this ball with a thread. You see, I have tied this ball with a thread. Now, when I rest this ball upon my hand, I feel the weight of this ball. However, if I hold the ball with my thread and if I just touch my hand with the ball, I don't feel any weight, but I'll just feel that the ball is touching my hand. I won't feel that the ball is heavy anymore. If I do that to a very heavy object, let's say I have a set of magnets placed with me right now. This is very heavy though. Imagine this weight. This is very heavy. When I place it on my hand, I feel the weight of this object. But when I hold it up in the other hand and just touch it over my left hand, I don't feel any weight being experienced upon my left hand because all the weight is being taken by my right hand. So the concept of weight is more or less relative. It depends upon whether we are exerting a reaction force by bringing in a resistive force towards the object from falling down. Well, Tejas, why don't satellites and astronauts fall down if they are in space and they are pulled down by gravity? To answer this question, we have to know what is called as free falling. Actually, all the satellites and astronauts who are in space are continuously falling towards Earth. But they also have what is called as the side velocity. When I take this particular ball and when I throw this horizontally, you see that the ball does not simply fall down. It goes forward as well. Similarly, astronauts and satellites that are in space, they just don't fall down. They also have what is called as a side velocity. If we are looking at it from the front, they also have something called as the side velocity. So just like this ball, which can go forward and also fall down, we have all these objects, satellites and astronauts, they are also moving forward and are also falling down at the same time. What happens if I throw this ball so hard that the curvature that it takes becomes nearly equal to the curve of the planet? That is, we know that the earth is spherical in shape. If I throw this ball so hard and so fast that when it is falling down, that is taking a curve, it matches the curvature of earth, this ball keeps on falling forever. This thought came into mind of a scientist called as Isaac Newton. He was the one who gave us the concept of gravity. He questioned why do things that go up come down, and he got an answer and he called it as gravity. He also came up with an experiment called as Newton's cannonball. In the first image, you see that a cannonball is being shot from a very high mountain, whereas when it is being done so, you find that the velocity of the first cannonball is very slow. That is, it is being thrown very in a very slow fashion. That's the reason it is not going much forward. However, in the second image, we find that the cannonball is being shooted at a higher speed. So it travels a further distance and covers the curvature of the earth. However, in the third image, we find that the cannonball is being shot at a very great speed that it takes a curve all the way around the earth. Now let's watch a video by Matt J. Carlson, who prepared this video for TED which explains how free falling works in outer space. As I explained it to you earlier, astronauts feel weightlessness in space just like how we swim in water. So, all objects in space, including astronauts and the satellites, they all orbit around the Earth in what is called as a free fall state. That is, they're always falling towards the Earth. Then why don't they come back to ground? If that is your question, the answer is orbiting. Newton came up with this concept of Newton's cannonball, and that is what is being explained in the video right now. You find that the cannonball which is shot with a greater velocity covers a greater distance. However, if we shoot it with a very high velocity, it can go all the way around the world and come back to us. Consider the satellite which is at the top of the earth. So, if there is no side velocity, it will just fall down. However, if it has a sideways speed, that is sideways velocity, it will go towards the side as well as fall down. So when it is going towards the side and also falling down, Earth is trying to pull it back towards it, which causes it to go towards the side again and fall down towards the Earth. And again, it goes up, back, being pulled back towards the Earth again. And there is also the sideways velocity, which pulls it back again towards its top position. So basically, this particular satellite keeps going around the Earth always, that is in a state of continuous free fall. That is how both astronauts, satellites, and the International Space Station all go around the Earth in under a state of continuous fall and still don't fall back to Earth. Isn't that amazing? So imagine this, even if you stand upon Earth, if you can throw this ball with a very, very, very high velocity, you'll be able to make this ball go all the way around the world and come back and hit your head at the back. However, there is a problem. There is something called as air resistance. When we throw this ball in the atmosphere, the air in the atmosphere tries to resist the ball from going forward. That is the reason why we are not able to. That is the reason why we can't achieve such high velocities by throwing by make objects to go around the Earth at a very low altitude. At higher altitudes, we don't have much air resistance, and that is the reason why we place satellites and astronauts we find satellites and astronauts being placed around in orbit around the Earth at a very high altitude. Okay, this is your favorite cartoon, Richie Rich. Let's watch a video from Richie Rich, which shows how he fires a golf ball all the way across the world along with his cousin Richie. Can you?
We now continue with the Richie Rich Show.
This new super golf ball Professor Keenbean invented is supposed to really travel. Yeah, well, we'll just see. Where'd it go, Richie? I don't know. I couldn't follow it. Huh, some super golf ball. It traveled a whole foot.
Wow, that was a really good video. See how Richie was able to get the golf ball all the way around the globe by hitting it so hard? Yeah, let's move on with our class. Well, most often you would have looked in when you watch cartoons, you find that whether it might be Tom and Jerry or the Roadrunners, you find that they don't fall down until and unless they look down towards the earth. Does gravity act upon us only when we look down? Well, that is really wrong. Gravity always acts upon us whether we look down or not. Well, this ball does not have any eyes. Does that mean that if this ball does not look down, it won't fall down? It is not the case. Gravity always works irrespective of whether that's a living object or a non-living object, whether you look down or you not. So this concept of creatures or characters not falling down in cartoons when without looking down due to gravity is actually false. So know that even if we don't look down, we fall due to gravity, and gravity always does its work. Ages, we are talking about weightlessness a lot. Is there a way to experience weightlessness only on Earth, just here on Earth, and not in space? Because I can't go to space with rocket, and my mother will not give me permission. Actually, you all have experienced weightlessness. Do you want to know how? I'll answer you how. If you have jumped up high, that is, when you have jumped up from a very high altitude to a lower region, taking a curved path, you would have experienced a brief moment of what is called as apparent weightlessness. That is, you would have felt very light when you would have jumped from a very high altitude. And you also see the ballet dancers performing what is called as a high lift jump. When they do that, they feel very light because for a brief moment of time, they don't have any resistance force acting upon them except that of a minimal resistance by the air. And when you're traveling down using an elevator, you would have felt some a hunchy kind of sensation in your stomachs, isn't it? That hunchy kind of a sensation that you feel in your stomach while you're traveling down in elevators is also what we experience as apparent weightlessness. You all must have gone through the roller coaster rides, right? So during the roller coaster rides, when you're traveling up and down, during your upward journey, you feel very heavy, and all the time you feel that you're going back. But when you're going down the roller coaster ride, you feel very light, and you feel that you're being pushed away, and feel a sensation of floating, right? So, the downride of a roller coaster will also provide you what is called as an apparent weightlessness sensation. This weightlessness sensation can be experienced here on Earth, not just using the roller coasters and not just the elevators. There's also another method for experiencing apparent weightlessness here on Earth. You want to know how? Yesterday, you all learned about aeroplanes, right? People who want to train themselves to go to space or want to experience weightlessness, they go into planes that give them what is called as the zero gravity or microgravity experience. That is done. How is it done, Tejas? Can you explain it to us? Yes, I will. Consider an aircraft. While the aircraft is going up and all the passengers are seated in, it takes what is called as a parabolic path. That is, this aircraft goes up and dives down, just like a roller coaster. So in roller coaster, you all would have been belted with the seat belts. But whereas in these aircrafts, they will be bounded with what are called as, the sponge sheets to protect you from getting hurt. So you will be laying across the bed of these planes, and when the plane is going down, for a brief moment, somewhere close to 15 to 20 seconds, you feel very light and you will be able to float within the aircraft. So you get to see these pictures of the people who are experiencing these weightlessness experience in zero G planes. Let's watch a video and learn more about how these aeroplanes work and how we will experience weightlessness in these planes. Can we have the video, please?
So we went to San Jose because I got a ticket to the Vomit Comet. I had to get up at 6 a.m., so I was fucking excited. A zero-G flight is an airplane that does parabolas, so it goes up really fast and then down really fast, so you get to experience what it's like to be weightless. I was really freaking nervous about it because a lot of people do throw up, and if you throw up, you have to get back in your seat for the rest of the flight. So basically, it'd be the most expensive vomit of your life, unless you threw up into somebody's Gucci bag. For each parabola, you get about 30 seconds of weightlessness, and we did 15 of them, so I got about 7.5 minutes of glorious weightlessness. So without further ado, here's some footage of me having the freaking time of my life. So I was supposed to narrate this as it went, but I could get no intelligent commentary out of myself. I have no idea what to say. Yeah, that's about it. As the airplane is going up, you're laying down on your back, and first you're getting heavier and heavier and heavier, but then you're getting lighter and lighter and lighter until you just float up. It was really like flying, and your body doesn't really know what to do. Your instinct is to just pedal, which is terribly ineffective. Oh my god! They threw out some water, and we got to catch some candy. I feel like fucking Pac-Man.
Okay, that was an interesting video. Now, you see astronaut Scott Kelly playing with what are called as water balls, and he's playing the game of ping pong with water balls instead of using a normal ball. In space, we find that as everything is being pulled in an equal amount in all directions, we find that there is nothing to resist the water from going into a teardrop shape. So that is the reason the water droplets, all that have fallen out of the bottle, they come together to form a spherical shape, and they don't detach from each other. So using this particular concept, astronaut Scott Kelly, is playing ping pong ball with the water ball that he has created in the International Space Station. Isn't it cool? Like how they get to do different kinds of experiments in international space stations. It truly is a wonder of gravity. Well, most of you are confused with the concept of the difference between mass and weight. Most of you want to know that how paper planes fly and why not book. Well, the answer is very simple. As paper plane has more lesser mass, the pull that it experiences by the earth is comparatively less. As book has more mass, that is more substance in it, the force experienced by a book due to the pull of the earth is much more. And the air resistance also prevents the paper plane from falling down, whereas the book can overcome air resistance, but paper plane cannot as effectively as a book. That is the reason why paper planes can fly and books cannot. I hope you all understood the topic about how astronauts float around in space, what is gravity, and how astronauts train themselves to go to perform different experiments on using microgravity conditions, and even though why they don't fall down towards Earth even if they are in orbit. Now we'll take few questions from the kids section in the chat box to give you more answers and to clarify all your doubts. I request Zubiya to join me on the screen to clarify the doubts of the kids.
Thank you, Tejas.
Okay, was that astronaut Abby? No, it was the astronaut's name was Scott Kelly. He had spent more than 300 days in space continuously working in the International Space Station. What other questions do we have here in the chat box?
I
What
can.
happens? Okay, there is this question. What
Hmm.
happens to the objects if their velocity or speed comes down? Do astronauts fall down to Earth and satellites fall down to Earth? Actually, yes. If there is a change in their position or if there's some decrease in their velocity, they start falling towards the Earth. In order to overcome these faults, scientists and engineers build what is called as an in-house propulsion system, which takes these satellites to their proper position if they are altered from their original position, so that they continue to keep orbiting Earth and don't fall back to Earth.
I would like to take this question. We have a question that when we bounce a ball, it goes down and it comes back up. So when we jump, why don't we come back up? The reason behind this is when we drop a ball, there is some elastic force in that ball, and due to that elastic ball, there is. Uh, would you like to help me with it, Tejas? That
Yeah,
when we
sure.
drop the ball,
Okay. When we consider a ball, when we drop it, it experiences what is called as a rebounding force. So this rebounding force, that is the reaction force, which comes from Newton's third law, will cause the ball to go up high. However, there's some amount of energy that the ball loses. That is the reason why with each bounce, the height to which it bounces comes down. Whereas when it comes to humans, that is us, when we jump up high and come back down, the force exerted by the earth upon us, the reaction force, is taken in by the fluids. This is called as suspending. That is the whisk. The fluids in our body and this the body itself will damp the force. That is, when you consider a sponge ball, you will be able to squeeze it, right? It is not a perfect rigid body, and that is how even when humans jump, all the force that the earth exerts back on us will be damped. That is, it will be dissipated, so we don't jump back again. So the force that the reaction force that the earth exerts on us is absorbed and dissipated. Why do we fly in space? As we told you, in space, that is while astronauts are orbiting, they don't actually fly. They are under the state of a free fall motion. Let me explain it to you in an easier fashion so that you all can understand. Right now, let us consider that I have a ball, I have a tape with me. Tape move along with my eyes. As in, when I move, my body, if they move along with my eyesight, I find that the ball and the tape is stationary with respect to me, and the background is moving, although it is me who is moving with respect to the background. The same case happens when it comes to space. That is, even though the astronaut is falling down continuously, the space station or the spaceship in which the astronaut is, uh, even that is also under a state of continuous fall. That is, even if I'm falling down, the wall behind me is also falling down with the same speed. It is just like elevators. When you when you go travel in an elevator, you see that the walls, the number panels, everything start moving down with you, along with you, and you don't feel that you're actually going down, you're actually falling down, you don't experience that. However, you see that after some time, when at first you were in somewhere around in 10th floor, after some time you'll find yourself in the ground floor. So that is how you feel that we are not falling in space, but actually you are under a state of continuous falling around the earth. But even before you fall down, earth actually curves so that you start falling again towards the earth and it starts curving again. This process keeps continuing, and that's the reason you keep orbiting the earth. Gravity is the force which attracts two bodies having masses. Okay, correct. Do we have any other question?
Yes, they asked a question that paper plane. We they asked that paper plane can fly, but if we fly a book, then it falls down back to ground. So we answered that because paper plane is very light in weight, so the gravitational pull which attracts it towards the ground is very less on the paper plane as compared to the book. But now they are asking that how come the normal plane, which has very much mass, very much weight, so how it is able to fly in sky? They are asking that
Okay,
question.
I'll explain that to you again. As I was demonstrating to you earlier, let you see that this set of weight. It is very heavy, and I have tied it with a thread, and I'm holding it in my other hand. So this I'm trying to pull them up so that they don't fall down, even though they are heavy, and though this ball is lighter than these set of weight scales, the ball will fall down and the weight will not, because the weight is being held by my hand. Similarly, when it comes to aeroplanes have what is called as lift. The lift that is produced by the wings pushes them up, it takes them up, and the force that the lift exerts is much greater than the pull that is exerted by the earth. When the lift force becomes lesser than the pull exerted by the earth, we find that the aircraft comes down and crashes down. That is the reason why when the wings are not able to when the wings are incapable of producing sufficient lift to keep the aircraft up in the air, we find them crashing down towards earth. That is how we see most of the aircraft accidents taking place. What other questions do we have? The kids are very enthusiastic. They are coming up with many curious questions.
We'll try to answer it all.
Okay. So even as we all spoke to you about, the total weight of the object, or the weight it experiences is it's dependent upon the contact forces that resist the object from falling towards earth. So if I take a weighing scale and if I place it at the bottom, and if I don't actually place this weight upon the weighing scale completely and release it, I won't be able to measure the actual weight. If I just touch it over the plate, I won't be able to measure the actual weight. So, which means that I'm exerting an upward force, cancelling the downward force, which the weight is actually, which it has to exert on the plate that is at the bottom. That is the reason it is the net force that is acting on the body that will give us the sensation of how much weight it would experience. So, similar to the game of tug of war, if there is no person that is pulling you from the other side, you won't feel any resistance in pulling the thread. However, if there is another person who's trying to pull the thread or pull the rope from the opposite direction, you'll have to apply same amount of energy or even more to pull them towards your side. So, in order to go away from Earth, that is to escape from Earth, you have to exert a force which is much greater than the pull exerted by the Earth, keeping us all down. We float. Okay. We float. That is.
Tejas, I have one question. How come plastic ball bounces, and why does it come back to the ground when we drop it down, and then why does it comes upward again?
As I told you, it's something called as when we talk about the rigid bodies, the body goes down. It experiences what is called as the reaction force from Newton's third law of motion. That is, when an object hits the ground, it experiences a reaction force in the opposite direction. So, as Earth is stationary, as the ground is stationary, that force is transferred to the ball. From the ground it is transferred to the ball, so the ball pitches up. But when we go up and when we jump down, the force that is transmitted to us uh, will be dissipated. That is, if the sponge ball, when we hit the sponge, or else let's consider a clay, when we hit the clay towards the wall, it won't bounce back as much like a plastic toy. The reason is that it would deform completely. It is not a rigid body. It is it is a plastic, it loses its shape. So depending upon the damping coefficient, that is how much a body damps, uh, the reaction force, how much it is being damped by the body, that decides whether the object bounces back or it does not. Okay.
Okay, Tejas, I have one another question. Do satellites require fuel to orbit around the planets, or just their gravitational pull itself is enough for them?
Actually, once an object is placed in an orbit, it does not need any fuel to go around the Earth, because it is from Newton's first law of motion that an object in state of rest will continue to be in that state, and an object in state of motion continues to be in that state of motion until and unless an external force acts upon it. So, when we consider that there is no external disturbance that is pushing these satellites out of their orbit, satellites don't need any fuel to go around the Earth. Whereas they need fuel, that is, they need energy to perform operation, to communicate, and to send information back to the ground. This energy is provided by the solar panels that they have. They provide the electric energy that the satellite requires to go around the Earth. However, we find that it is not always the case. Satellites face something called as uh, traction forces. These traction forces change the orbit of the satellites. It is due to the resistance it faces due to the magnetic field, or might be due to the atmospheric turbulences. There are many reasons why how external forces disturb the position of a satellite. To overcome that, we have a very small few propulsion system placed on the satellites to correct their orbits.
Tejas, thank you so much, Tejas. It was very great, and I got so much of information from this.
Okay, thank you, Zubiya. I hope kids have learned all about gravity and all about weightlessness, how astronauts are able to float around in space. If you do have any questions, do feel free to post us, send us questions in the chat section. And today we won't be having any homeworks so that you all can enjoy. And in the resource section, we have shared few video links that will give you more idea about what is weightlessness, and that will give you idea about what is gravity, and how as what kind of fun astronauts have in international space station while they're experiencing weightlessness. Tomorrow we have a session on life beyond Earth. If you want to know how Timo the alien that you all met in the first 2 days, if the friend that you made, how she comes from, where she comes from, how will be life beyond Earth and on different planets and different galaxies, what are the possibilities. If you want to know about all these things, come back tomorrow here at 6 p.m. and we'll have the class on the same platform. And you all have been doing very very good on your assignments. All your homeworks have been so good that we are very happy to correct it. And I hope that you are done with your yesterday's assignment of drawing the aeroplanes and coloring it and marking the parts. So that's it for today. This is Tejas along with Zubiya signing off for the day. Bye bye.
Bye.